This is the bit then that you've all been waiting for. Why is water quality so important? And it's all to do with precision and accuracy. To obtain accurate results, we need consistency. So if we look at what precision and accuracy is, this is something where we have good accuracy. The results are very close to the target result, they're very close to the bullseye, and they're precise, they're very tightly grouped. This is imprecise, that they are scattered about here, but if we were to average them out, they would actually come out to be quite accurate. With this one, we have good precision, that they're grouped tightly, but they're way off centre, they're way away from the bullseye. And this is where we have poor accuracy and poor precision. We need good precision in order to have any chance of getting good accuracy. And in order to obtain precision, we need to have stable conditions in the HPLC. We need to have stable retention times, we need to have stable peak responses. And for that, we need very high levels of consistency in all areas of the HPLC method. And the method we met earlier on, very complex, lots and lots of potential variables in there. Any unknown material that we add or introduce by the water adds an additional variable that we are not controlling. And there are various types of contamination that we can add in. The first is organic contamination, and it is detected by most detector types, and it can show up as extra peaks in a chromatogram. So if we look at green as being a normal chromatogram, if we have contamination, we are introducing additional material in through our water, which is then generating an extra peak in a very complex chromatogram. Very easy to misinterpret that. That might come off on top of a substance that we're interested in. It could boost the area, all sorts of problems. We don't want to introduce any additional contamination. It can also cause high levels of background noise. So if this was using water that was very pure, particularly with isocratic methods, if the water contained organic contamination, then we would get high levels of noise. And if we remember back to sensitivity, if we're working in trace analysis, high levels of noise mean that we will get very, very poor precision on our results. So we want to keep our noise level at a minimum. So let's look at some specific examples. And this is where we have extra peaks that are being introduced in the diluent. So if the contamination is eluted within the chromatogram, this results in extra peaks in all the chromatograms. And it's quite common if the cause of the contamination, the root cause of the contamination, is where we have introduced that in the sample diluent. So it is in every injection vial that the autosampler is injecting. And it tends to elute as extra peaks. So we look at a normal chromatogram, we have our 2 peaks here, and if we then have contamination present in the diluent, then we now have an extra peak that's appearing in our chromatogram. We don't know what that is. There are certain circumstances where we would have to identify that, which is a huge amount of work, and we're just better not introducing that peak in the first place. Quite often though, the substances that we introduce don't elute within the runtime, so within the 5 minutes that we're acquiring the data for that sample. And if we look at that and what goes on, we have our sample that's injected, it's introduced some contamination in, that's moving very slowly through the chromatogram and it's spreading out all the time. So this is our target analyte, that's all fine. Next sample gets injected, target analyte moves through, we get a nice normal looking peak chromatogram for that. All the while the contamination is slowly making its way through. Another one we inject, nice looking chromatogram, all looks fine. Inject another sample and then this material here, this big blob of unknown contamination comes out, huge big blob, comes out on top of our target analyte. It's made a mess of our chromatogram, and that if that's part of a sequence, that can easily ruin an entire sequence worth of results if this peak comes out in the wrong place. Very, very difficult to troubleshoot as well. It can be very difficult to find out these things because the material comes out in this injection, but it was actually introduced 5 or 6 injections previously. One of the common ones that we see is organic contamination that is introduced in the water that we use in gradients. And if the contamination is eluted within the chromatogram, this results in extra peaks in all chromatograms. Very similar to the types of problems that we see if it's introduced with the diluent. But the difference here is that we will observe peaks even when we don't perform any injections, and that's one of the ways that we troubleshoot these things. So if we look at a normal chromatogram, again, 2 peaks here, and then the contaminated chromatogram, again, we've seen an extra peak in here. Very similar to what we've seen when we inject in the diluent, so there's quite a bit of work and time involved in actually troubleshooting and trying to get to the root cause of the source. We just don't want to introduce that in the first place, and one of the ways we do that is by using very, very pure water with very, very low levels of contamination. Very small amounts of contamination, the HPLC system will pick it up. It's a very, very sensitive method of analysis. And if we look at this as an animation, we can see that the beginning of the gradient, just water going through it, is bringing contamination which is building up. We inject the sample on, we're running the gradient up, increasing the organic, stronger and stronger. At some point our material is going to start to move. Critical point, starts to move across, and then we end up with this huge extra peak in our chromatogram that's been introduced by the water loading it up at the beginning of the gradient. And when we start the next gradient, exactly the same thing is going to happen, that we have cleared the first lot off, we're now building it up again, we reach the critical threshold of organic, and then we elute the contamination and the target analyte. So every time we do an injection, we are going to end up with extra peaks in it. In a sense, that's the easy one to troubleshoot because we see it in every injection, but there are examples where we get material that is a late eluter. So that's material that we're building up with the water, but it takes longer to come out, and it's often no longer peak shaped, and it just looks like some random blob in the chromatogram. So again, a normal chromatogram, inject another one, and perfectly normal looking chromatogram, we keep injecting, and then all of a sudden we get a chromatogram that just looks wrong. Now this material has probably been built up by the mobile phase, the water in the mobile phase, very strongly retained, or we're not using mobile phases that are strong enough to elute that within the 10 minutes that we're acquiring, and it takes maybe 50 or 60 minutes for it to come out, and it no longer looks like a peak. And then the next injection is fine. Very, very difficult to troubleshoot. It just looks like a random problem, but it's usually not. If we have a contamination that doesn't elute at all, and it continually builds up in the column, the stationary phase starts to degenerate, and there are lots of problems that we see when the stationary phase degenerates. It's very common with isocratic methods because they have a fixed ratio of organic that never gets to be strong enough to elute this material off. And when we look at the types of problems, we can see a decrease in separation. So that would be a normal chromatogram. Reasonable resolution between here, but now we're starting to see the peaks get closer together. It can be subtle, but eventually it'll get to the point where our two peaks no longer resolve. And another common one is that we get a distortion in the peak shape. So in this case, nice sharp symmetrical peak, but here the peak's fronting. The material's got a sharp, blunt front on it, or tailing where it's starting to do. Lots of other weird and wonderful shapes that we see in peaks when the column is starting to degenerate. And we can also see steady shifts in retention time. The peaks might gradually start to become later or sooner and drift out of retention windows that allow us to qualitatively confirm the presence of a substance. With organic contamination, we can also end up with noise, particularly in isocratic, that the UV substance is present in the mobile phase, it's there all the time, it absorbs, it generates high levels of noise, we get poor sensitivity, and we get, so that's our noise giving us poor sensitivity, or we get poor baseline stability, so it randomly wanders about. Neither of these we want. We want a nice, flat, stable baseline with low levels of noise. So organic contamination present in usually the water causes all sorts of problems within the HPLC. Within organic contamination, it can cause problems as well. It alters the pH of the solution, and that then causes the compound to ionise in a different manner. That affects retention time because the charged version of a molecule retains less than the uncharged version. So if the pH is being altered, it affects the ionisation, it affects the stability of the retention time. When we have a mass spectrometer, it also affects the signal in the mass spec because the mass spec only sees ions. And inorganic contamination in the mobile phase contaminates the mass spectrometer. Inorganic material is normally non-volatile. The mobile phase gets evaporated, but we leave behind this solid, inorganic, non-volatile material that very quickly contaminates the mass spectrometer. Inorganic contamination also can cause reactions with the substances of interest. It can degrade them, it can chelate with them, or it can adsorb. And we get all sorts of problems with chemical reactions that inorganic substances form with our target analytes. So if we look at an example of an inorganic substance causing an effect on pH, we can explain it this way. So for our substance here, this bit, the uncharged bit, retains longer than this does. And similarly with an acid, this bit retains longer than this does. This is a much higher affinity for water. Inorganic causes inconsistencies in the pH, so it will move this reaction backwards and forwards randomly, and that causes shifts in retention time. And this is how we would see that manifest in a real set of data. So normally we would expect very, very stable retention time. And you can see this is pretty typical data that we see that our standards here, our samples, all our standards, everything has a very, very stable retention time. If the mobile phase pH isn't being controlled, or we're introducing inorganic substances that affect the mobile phase pH, then we start to see the retention time precision start to wander about all over the place, and really that data is meaningless. And it can be as simple as just a small amount of inorganic contamination going into the mobile phase can cause these types of problems. With mass spectrometry, we see the effect that pH has on the signal. So again, if we had a run of standards and samples, all the standards should give us a very, very similar area count, and all the samples should give us a similar area count as well between the samples. And we would expect this degree of stability in the signal in the peak areas between standards and samples on UV, on mass spec, and any type of detector. Very, very small amounts of inorganic, particularly with mass spectrometers, can cause data to look like this, where our precision just is all over the place, that we should be seeing something nice and precise like this. But these areas now are meaningless. They're so variable that we can't tell any information, any quantitative information from it at all. So again, it affects pH, and this affects the signal this time. And because the mass spec only detects ions, anything that affects the production of ions causes instability in that signal, and this is what we see. And it's very, very common in mass spectrometry that we see problems like this. And one of the main ways that we control it is making sure that the pH of the solutions we work with are very stable, and we need to use very clean water to make sure that we're not introducing inorganic contamination that will affect pH.